Okay, thank you. So I'm not a user of the ROPOL data, but I follow the team's activity very closely because ROPOL is a really successful example of how to make small telescopes work efficiently. And today I would like to present some new observational and technique approaches that may be useful for this project. So in Special Astrophysical Observatory, where I work, the AGN monitoring is conducting for more than 30 years, and it includes many methods aimed at studying the AGN central regions or the central parsec. Today, I will talk about two polarimetric methods initiated only a couple of years ago, which not only give results, but are also effective even on small telescopes. So I'll start with the vibration mapping in polarized light. The method is based on the fact that in a large number of Soviet I galaxies, the radiation from the central regions, broadline region plus accretion disk, are equatorially scattered on the dusty torus. But the size of the dusty torus is poorly known, only from the infrared estimates, and it affects the accuracy of estimating the mass of the central supermassive black hole using the spectropolarimetric method initiated in 2015 by Afanasyev and Popovich. And to improve the accuracy, we decided to use polarimetric vibration mapping. The method was originally proposed more than 10 years ago, but the observational test failed due to the use of the broadband filters, where many polarization mechanisms are mixed together. Offering the usage of polarized radiation only from the broadline region, or only from broad emission line, where the equatorial scattering is the unique polarization mechanism, we removed all these problems. And the method was tested on the observations of the Soviet I galaxy, Mark 6, for which the spectropolarimetric monitoring was carried out in 2010-2013. The delay in the polarized emission line was about 100 days, which coincides with the theoretical predictions and was 2 times less than the estimate by infrared interferometry. We assume such difference can occur due to the fact that the maximum brightness temperature in the infrared band is located at greater optical thickness than the dust sublimation radius where the equatorial scattering occurs. And this method requires more detailed numerical calculations, but it's already clear that it can give new information about the inner structure of AGNs. However, spectropolarimetric monitoring is very expensive in terms of the telescope time and requires really large instruments such as the 6-meter BTA telescope. And because of this, we started polarimetric monitoring of Soviet I galaxies and narrow band filters covering only the emission line and the continuum near to subtract all the continuum polarization mechanisms. And we initiated it on several small telescopes 2 years ago, and the project still goes on, and we're waiting for the new results. And unlike Soviet I galaxies, the blazar's polarization has synchrotron origin. Our team's interest in this type of objects began with the blazar S50716, a very bright, very popular, and very variable source. For the first time, we conducted long-term monitoring in 2018 and found a 1.5-hour period. The same period was typical both for variations in the total light and of the variations of the polarization vector direction on the Q plane, which characterizes the linear size of the emitting region as 10 astronomical units. And this is the intraday EVPA rotations, which is also crucial for the theory, as I believe. It turned out that the variations in the brightness can be well explained by the change of the Doppler factor. And all this prompted us to make a simple numerical calculation, remember that we're primarily the observers, of the change in polarization as plasma rotates in the helical magnetic field in the jet. By adding precession, we were able to explain the pattern observed in the Q plane with a good accuracy. But we also need more detailed theory than the simple geometrical model. And again, such monitoring requires a large amount of telescope time, which is very difficult to obtain with the large instrument. However, using 2 basic principles of polarimetry, we allow this to moved to small telescopes. And these principles are the differential polarimetry and the usage of such an analyzer that gives you two Stokes parameters describing the linear polarization simultaneously. And then the accuracy of 1/10% that is crucial for the AGN polarization become possible. Since there had been no device with a polarimetric mode on the 1 meter SAO telescope, we created a Stokes polarimeter. This is a very simple device with two operational modes. In the photometric mode, there is a field of view of 5/6 arc-minutes, and also the polarimetric mode. And in both modes, the two turrets of filters can give you totally 18 positions for the filters. So also here we use the double Wollaston prism as an analyzer, and although due to the presence of the inclined mirror, the instrumental polarization is non-zero, is about 0.7%, but it is constant of the field, and these variations don't exceed 0.1%. Also, the observations of the standard stars also show that the instrument can achieve the desired accuracy of 1/10%. The first light of the device took place in the January 2020, and we started by repeating the same observations of Blazer S54716 again. To our delight, we not only achieved the needed accuracy, but also the same 75 minutes periods of variations in both total light and the polarization direction. And however, such a device is pretty good for us, but for us, it didn't seem enough. And 6 months later, we started working at the new generation device named Magic, along the project of the AGN monitoring that we do. And now Magic is the successor to the STOP. The device is now in the test operation, so I won't talk much about it. And its main features are the presence of the spectral mode and large field of view, about 13 arc-minutes, and the usage of the original double Wollaston quadruple prism. Now the field of view in the polarimetry mode is not limited by a small rectangular mask, but is a full size of 6/6 arc-minutes, which is very crucial when you need to have local standard stars in the field of view of the object. So for sure,
3 more minutes.
Okay. For sure, as a test of such a big field, we observed the polarization of the continuum radiation of the Crete nebula. And this test showed that the variations in the instrumental polarization of the field correspond to those required for the polarimetry of AGNs as weak sources. So this is the end of my speech, and I hope that the experience of our team in methods and studying of AGNs, as well as in the device construction, will be useful. Thank you.